Okay, students, so my long hairs are gone now, and I have a shorter hairs and a haircut after 1 year. Right. So now we start lecture 3. And if you remember from your lecture 4, lecture 2, we were talking something of system components. Now, so we know now that the system components essentially, it tries to tell you about the number, the minimum underlined, the minimum number of components or molecular formulas or molecular species that you may conceive of to describe the chemical variability of the system, which essentially involves multiple minerals. That's all what it's all about. So that is what a system component is. So in the last class, when we ended the last video lecture, we were talking about Al2S, sillimanite, kyanite, how we find out the chemical composition of a system. Now, there can be complications. And I will first elaborate a little bit more about system components, and then they will switch on to something new. Say, for example, the first and foremost thing that you should remember is, say, for example, someone asks you, what is the system component of quartz? Now, the first impression that you get, quartz means SiO2. Yes? So you imagine that quartz contains SiO2. And that constitutes 100% of quartz. But it is not right. It is not right because there are components that are there in quartz. If you analyze quartz with a proper instrument which is standardized for elements perfectly, you will see that quartz contains some elements that you don't think you will have. But because we have been told repeatedly in the past that quartz means SiO2, we tend to forget that there could be other minerals. Sometimes these minerals impart color to quartz. So you have red quartz and blue quartz. So these are some of the things that you have to be very careful about. So when somebody tells you, find out the system component, the next question that you should ask, what is the composition? If he says quartz, you ask him, what is the composition of quartz? Is it pure SiO2 or there are some other components? Now, if a teacher had asked you the question and this was your answer, he would be happy right there because he knows that you have understood it. But if you don't ask, first impression is you will not get the answer right. So before you find out the system component, ask for the composition of the mineral. So your system components will be dictated by the compositions of the minerals. The actual compositions, not the composition that you have in mind. Say for example, if you talk of muscovite. So muscovite has the formula Kal2 AlSi3 O10 OHO twice. Now that is an ideal composition of muscovite that we have been taught. But if you go into the details of chemistry of muscovite, you will see that this is completely untrue. Completely untrue. For example, there is some amount of sodium in muscovite. Sodium Al2, AlSi3, O10, OH12 whole twice, it is called paragonite. So sometimes you have small amounts of paragonite within muscovite. Now you have to know, before you start your finding out the composition of a system, that all the minerals that your teacher told you or someone told you, whether you have got the compositions of those minerals precisely written down in the question. That is very, very crucial. So say for example, sodium is an addition, then for assume chromium is another mineral that goes with aluminium, which is in that octahedral side. This is the octahedral side, this is the tetrahedral side. There are 2 octahedral sides and 3 tetrahedral sides, apart from potassium and sodium, which go into the larger 9-fold coordination. And then some ferric ion substitutes aluminium. An OH radical is replaced by fluorine and chlorine. And in addition, some of this little muscovite could also contain a little bit of salt calcium T+. Now this formula is an idealized formula. It may not be the composition of the muscovite that you're seeing under the microscope. Have you understood? So it's very, very important, if you have to find out the components, system components of a system that contains muscovite or some other minerals, then you have to see the composition of the minerals corrected precisely in front of you. Otherwise, everything that you do subsequently will be completely wrong. And this is how to go about the problem. Right? Now, this type of examples can be given for all minerals. Say, for example, I draw a tetrahedron. Say, for example, this is CaSiO3, this is MgSiO3, and this is FeSiO3. This is called the pyroxene-pyroxenide triangle. And if you take the midpoint of it, which is CaMgSi2O6, this is what is dioxide. Similarly, if you have CaFe and Si2O6, then this is called Heidelbergite. So this is your very famous pyroxene quadrilateral. Pyroxene quadrilateral. But this is very idealized. This is very idealized. It is written as CaMg, Fe, Si2O6, which is 6-fold, 8-fold, and this is 4-fold coordination. But this composition triangle that I have given you, I don't know whether you know the name of this mineral. I think I should tell you this. This mineral is called it's called belastonite. This is called belastonite. So essentially, this pyroxene quadrilateral, which has been shown to you, which has been presented to you, and you're conversant with it, then your pyroxene should lie in this, something in this, so that it would fall in CaSiO3, MgSiO3, FeSiO3. These 3 are the components. But normally this is not true. Normally this is not true. Some amount of sodium goes into calcium site. Manganese goes into this site very commonly. Some of aluminium goes into this site, some of aluminium goes into this side, and there can be titanium, there can be chromium, there can be other elements that go into pyroxene to make up 100 weight percent. But say for example, this is an idealized formula. So if someone tells you enstatite, you will think this, yes, idealized MgSiO. But this can contain calcium, this can contain aluminium, this can contain a little bit of sodium, this can contain a lot of other elements. So, before you find out the system component involving minerals, multiminerals, then the first thing that you should know is what is the formula given for each mineral. That is very, very crucial. So one more example to highlight the importance of system components. Say for example, Al2SiO5 is a famous formula of sillimanite, kyanite, and andalusite. This is a very famous formula of sillimanite, kyanite, and andalusite. This is an idealized formula. Why? Because chromium 3+, ferric iron 3+, goes into many of these solid solutions. Small amounts of sodium also go in. Now, sometimes what happens, these components may comprise a very small, minor or minute amount in this mineral, or they might comprise a large amount. Say for example, if you are taking a kyanite in an eclogite facies rock, those of you who understand it, kyanite in eclogite facies rock, chromium is a major component. Is a very, very major component in eclogite facies, that means high pressure pellitic rocks like containing kyanite. You know, kyanite is a high pressure polymorph. So normally the stable Al2SiO polymorph, not normally, always, in eclogite facies, the stable polymorph is kyanite, and kyanite contains a lot of chromium. So unless you know the composition of individual minerals in a rock, which is your system, you cannot find out what is the chemical composition, what is the system component of the rock. And that is very, very crucial and central to understanding metamorphic petrology. Don't wish it away. Don't wish it away. That's the central theme of metamorphic petrology. Now say for example, I ask you, what is the system component if a rock contains, let's make it simple, orthopyroxene, olivine, and quartz. I, as a teacher, ask you to find out the system component of a rock or a domain or a subdomain in a rock, whatever the system I have chosen. It doesn't matter. Orthopyroxene, olivine, quartz. I ask you to find out the system component. You're just going to ask me. You just should know that your teacher does not understand metamorphic petrology at all. Or he's either this, that your teacher does not know metamorphic petrology, he's asking questions, he doesn't know it, or he's playing the fool. He's just trying to see whether you really know it. If I ask the question, say for example, if I was in the Viva board, I would have asked you, can you tell me the system component of orthopera, olivine, or quartz, etc.? And seeing what is your response. I'm playing the fool. I'm seeing your response. What is your response? Your correct response is, so please give the chemical formula of the phases. And I know that you know. And I know that you know. If you have not asked me, you won't be able to answer the question. Because the formulas I have not written. So I cannot find out what is the system component. Now I tell you, orthoperoxin has the formula MgFe SiO3, that's orthoperoxin. Olivine, MgFe whole twice SiO4, and quartz SiO2. Now your teacher has played the cards. Now your teacher has played the cards. Since you asked him, so what are the composition of this system compounds? And he says that these are the compositions. Now you have to find out the minimum number of components that make up the system, which is a rock containing orthoperoxin, olivine, quartz, or a subdomain in a rock, a small subdomain of micron scale, where you have orthoperoxin, quartz, and olivine. So this is the point now. So what are your options? You can write, okay, Mg, Fe, SiO. You know Mg, Fe, SiO, so Mg plus Fe plus SiO, it's done. But you have then 4 components. But you could also write it as MgO, FeO, SiO2. And now it has 3 components. So you have MgO, FeO, SiO2 3 components, Mg, Fe, SiO 4 components. So this is my choice. Or, just say this, or you could have written MgSiO3, FeSiO3, SiO2. This would also do. Why? If I had written instead of MgO, FeO, SiO2 3 component system, and if I had written MgSiO3, FeSiO3, SiO2, which is also a system component, then it should be fine. But the question is, if I write it like this, so first SiO2, I can write it as 1 SiO2, MgO 0, FeO 0. So Mg, FeSiO3, yes, I can write MgSiO3, FeSiO3. But what about this one? It's very simple. Mg2SiO4 is the composition that you want to describe. So you have 2MgSiO3. Now you see 2Mg is balanced, silicon is now 2. So if I write, then it's okay. So these are my components which I have chosen. Right? And I can write my formula by algebraic addition of the 2 components. Right? So it's not that the number 3 is important. It's crucial. But these, the nature of it, is unimportant. It's for you, for your convenience, you could do it. But so long you're working with the number 3, fine enough. It's fine enough that you're working with this number 3. This is must. This or this. Or you could choose Mg2SiO4, Fe2SiO4 and SiO2. This is also correct. Have you understood? This is also correct. Because you can now write MgSiO3, 2MgSiO3 as Mg2SiO4 plus SiO2. It doesn't matter. So, the nature of the components are not important. The number of the component is important, thermodynamically. So, this is how system components are derived. It is not the nature of how many, but the number. That's important. That is important. Have you understood? So, now we know quite a few things. Conceptualizing, we know a system, we know isolated system, closed system, open system. We know now the definition of a system. It could be your choice, it depends on what you want. Then we know phase, then we know phase component, and now we know system component. And now we see all these things that I was telling you, all these things was telling you, and some of you must have think, what is Sir talking about wasting time? You will soon find out that I led you on the right road. Now we go into what is called the Gibbs phase rule. To understand metamorphic metrology, you have to know Gibbs phase rule. You have to know Gibbs phase rule, conceptualize Gibbs phase rule. I have already sent you the derivation. I think you have read it. It is essentially calculated Gibbs phase rule, which is famously given by the formula F is equal to C minus P plus 2. This essentially is called the degree of freedom. Degree of freedom, also called variance. Then you have C, which is the system component. And then you have phase, P, which is the number of phases. And 2, you know, stands for pressure and temperature. The variables pressure and temperature. So, you have the system, number of phases, system components, which is the minimum number of components, and the degree of freedom, which is also called the variance. What is variance? Variance is very easy to understand. Variance is essentially number of variables minus number of equations. That's it. Say, for example, I write an equation 5x plus 2y is equal to 4. 5x plus 2y is equal to 4. Right? What is the variance of it? If there was something called a variance. Number of variables minus number of equations. X is a variable, y is a variable. So, 2 minus 1 is equal to 1. What does this mean? That you have two variables and one equation. So that means one variable will remain undetermined, or you cannot find out x and y both from one equation. You cannot find out. You need, from this one equation, you cannot find out unique values of x and y. So the value, what is the problem? If the number of variables are 2, but the number of equations are 1, so you have a difference of 1, that means you need an input data. X and y both cannot be determined. Have you understood? You need an input data of either x or y to determine the other value. Have I been clear? Either you need a value of x to find y, or you need to have a value of y to find an x. There are two ways to do it. One equation will not give you, not allow you to quantify both variables. You will be left with one unknown. That is degree of freedom, and that is variance in metamorphic metrology. Essentially, number of variables minus number of equations. That's it. This can be done by two ways. Which can be done? We were talking either you need a value of x to find y, or you need a value of y to find x. So I can write, say for example, one case may be, I write x is equal to 2. Right? The value for x is equal to 2. So I have x. So in this expression, I will have 10 plus 2y is equal to 4, which means y is equal to 4 minus 10 divided by 2, that is minus 3. That is the value if x is equal to 2. If x is equal to 2, 10 plus 2y is equal to 4, that means y is equal to 3. What have you done? You have put in a value of x. Have you understood? You have put in a value of x. In metamorphic metrology, the degree of freedom means the system left to itself cannot find both x and y. It can either find, it cannot find x and y. You have to put in one to get the other. Information, quantitative information about the other. That is what is called a metamorphic variable. So this is one way. You assign a value that the system is not assigning. You either assume or you derive it from some other place and put it in there, whatever you do. But you have to do it. Or another way could be, you could write 5x plus 2y is equal to 4 and x plus y is equal to 1. So now what you have? You have now two equations. So it says 2 minus 2 equal to 0. Means what now? Now it says that, okay, with the information you have given, I get it, the system can find numerical values for the variables by itself. For the values, for the equations you have given, the system can find its value. You don't need to bother. You don't need to get something, some inputs from other. It is built in the system. So for example, how do you do it? So here, for example, y is equal to, will be equal to 1 minus x. From here, and you put it in this, 5x plus 2 into 1 minus x equal to 4. And so it's 5x plus 2 minus 2x is equal to 4. And so you can see, you can find the value of x. I have told this is A and this is B. Right? What have I done? In the first place, I have given a value x is equal to 2. Given a value x is equal to 2. And here I have added an additional equation. There is no difference. A and B looks different, but in concept it remains the same. Why? Because this is also an equation. X is equal to 2 is also an equation. And here x plus y is equal to 1 is also an equation. This was just only to tell you when we put in a value. When you put in a value means what? Put in a value for a variable. That's an equation. So A and B, although they look different, they're one and the same. Because here you have used an equation, here you have used an equation. Essentially no difference. Essentially no difference. Because you have two equations, your variance is 0 here. And if I had given you this only, 5x plus 2y is equal to 4, the number of equation would have been 1 and your variance would have been 1. That's the important point. That means when I talk of degree of variance, I'm trying to find out metamorphic variables. I am trying to find out the metamorphic variables that the system number of variables, you see, is not telling me which variable. It is telling me the number of the variables that remains unquantified. That is what variance is. Variance is the number of values, the number of variables that are unquantified in the system. The system by itself cannot generate the values. But it only tells you what is not there. It doesn't tell you how many variables it can find out. It doesn't say. It only tells you how many variables it can't find out. Have you understood? That is the catch of Gibbs phase rule. It does not tell you how many variables you can find out. It can tell you only the number of variables it cannot find out. The number of variables. Not even what is the variable. No. It says the number of variables that the system cannot determine. So those are the values you have to retrieve from somewhere else or change your system so that your f becomes equal to 0. That means whatever variables you give, it will be determined. But when you have f has a value, it means that that is the number of variables. And it doesn't tell you what is the variable. It tells you the number of variables that it can't find. It is about inability. It is not about ability. Degree of freedom tells the inability of the system to give you a particular variable. That is the important part. I hope I have been able to clarify the position, and this degree of freedom can be found out if you know your system components. Now you know, so there are minerals. I should know the compositions of all minerals to find out system compound. I should know all the phases, all the thermodynamic phases, and that may or may not include fluid phases that I told you before. And only when you do that, And plus 2 tells you how many variables remain unquantified. Tricky, no? Metamorphic petrology is philosophy. It has great philosophy in it. You have to understand it dead accurate. You will have no problem in understanding metamorphic petrology. You have to be dead accurate with your concept. That is why metamorphic petrology in India, for example, if you look at the geoscience fraternity, you will be going into research. Some of you will be going to jobs, okay? So those of you going to jobs, you will maybe not very much interested in other things, higher things. You can do it with whatever you will be trained for and your initial knowledge. But those who will go into research will find out that metamorphic petrologists per se and structural geologists per se who are regularly publishing in such journals at the highest level, that number is very small. It is because of the difficulty of conceptualization. Petrology, we had many metamorphic petrologists in earlier times. Now it has gone down and down and down and remains in only particular places in India. Very small schools which had a very strong history of metamorphic petrology. They have retained a bit, similarly with structural geology. Most people do geochemistry. Yeah. So, I hope we have understood this, right? Now it's time that we look at certain examples and try to make an example more and more complex so that you start finding out the difficulties in how Gibbs phase rule becomes the starting point of metamorphic petrology. Now, before going into Gibbs phase rule, I shall tell you a little bit about variables in metamorphic petrology. There are two types of variables in variables. One is called an intensive variable. Intensive variable. What is intensive variable? Variables that do not depend on the mass. Do not depend on the mass. Say, for example, refractive index, not metamorphic petrology. Refractive index, specific gravity. They don't depend on the mass. Similarly, pressure and temperature, they don't depend on the mass. They don't depend on the mass of the substance. Have you understood? And then, for example, mole fraction. Mole fraction it does not depend. Say, for example, you have a garnet with 20% almandine. That's the mole fraction of Fe in garnet. Now, you can have many garnets having the same composition. So, it does not depend on the mass, but it depends also on the masses of different components in the garnet. That's sure. But you can have, these are called the intensive variables. And what are extensive variables? These are just the opposite. Extensive variables. These are just the opposite. Say, for example, Gibbs free energy. Remember, Gibbs free energy. If you remember, G is equal to mu by N. What is mu? It's called the chemical potential. Oh, sorry, I have written the wrong way. Mu is equal to G by N. Yes. This is called chemical potential and this is called free energy. And G by N, that means molar Gibbs free energy, is called the Pinel potential per mole. So it does not depend on mass. So chemical potential is an intensive variable, but G is an extensive variable. So is entropy, so is volume, so, not volume, free energy, enthalpy, say for example enthalpy. These are all dependent on mass, but these variables are not dependent on mass. Molar volume, this is not dependent on mass, it's an intensive variable. So essentially in metamorphic petrology what we try to do is try to quantify the variables, and these are, I gave you a write-up on different chapters for you to read, and there they talk about the relationship between pressure, temperature, free energy, enthalpy, entropy, and so on and so forth. So then they essentially correlate intensive and extensive variables in it. But let's talk about variables in general. Well, now let's take this phase diagram. Andalusite, sylvinite, and kyanite. And this is called the triple point. This is equal to 505 degrees centigrade and 3.7 kilobar. Now, at crystal depths, 1 kilobar is equal to 3.3 kilometers. That means if you have a column of 3.3 kilometers of the crust, at the base of that 3.3 kilometer column, you get 1 kilobar pressure. So it's essentially H rho G. Height, H, rho, density, and G is the acceleration due to gravity. So 3.3 kilometers into the density, into the acceleration due to gravity, and then you get 1 kilobar pressure. So if you're talking of 3.7, then it is 3.3 into 3.7 kilometers. That is the depth. You can see it will be somewhere between 10 and 11 kilobar. So 3.3 into 3.9, yeah, it should be around 11 kilometer depth. So the triple point where kyanite, sillimanite, and andalusite coexist, it is roughly at 11 kilobars. You know brittle ductile transition of the crust, brittle at the top, ductile at the bottom, and you have a place where you have brittle ductile transition that occurs between 10 and 15 kilobars within the crust, depending of course on the rock type. But normally felsic rock, it's talking about based on brittle ductile transition, so it's somewhere there. So 3.7 kilobars is roughly around 11 kilometers. So it's the brittle ductile regime of the crust where the three polymorphs are going to form a triple point. Now we talk about Gibbs phase rule. Now, my first question to you, if I ask you, what is the variance of the triple point? And all of you will say, 0. Bullshit. Wrong. Why wrong? You forgot what I asked you to do. 0. No. Wrong. Calm and quiet. What you should ask the first question. You understand the triple point here means kyanite, sillimanite, and andalusite are the three phases. So I understand P is equal to 3. 3 phases up there. P is equal to 3. That I understand. But the moment I want to compute C, I have a question. I have to find out the system components. Minimum number of system components. And if I have to find it out, then the first thing that comes to my mind, what is the formula of your simplement? If you say Al2SiO5, that's for the pure number. If your teacher has that in mind, let him say it out. Let him spit it out. If the teacher tells you what is the triple point of the Al2SiO5 phase diagram, he's right. He's right. You see, I will tell you again. If your teacher asks you what is the value, what is the variance at the triple point of the Al2SiO5 phase diagram, means what? He has told you that all the phases, silverite, kyanite and lucite, they have the composition Al2SiO5 and nothing else. Have you understood? Mark my question. What is the variance of the triple point of the Al2SiO5 phase diagram? I told you that C is Al2SiO5. C is 1. He has told you this. But if he says, what is the variance of the triple point where sillimanite, kyanite and lucite coexist? See, something is missing. Find out the variance of the triple point where kyanite, sillimanite and andalusite coexist. He has not given you a crucial information for you. He has not let out the composition. His question is wrong. But if he said, as I said earlier, what is the variant of the triple point in the Al2SiO5 phase diagram, you can, of course, ask him what are the phases, but then it means you should go back to KG1. But at this point, for a first year student, he would not know. Really, he would not know because he has not been told. Yes, correct? So there are two questions. What is the variance of the triple point where where kyanite, sillimanite and lucite coexist? Is one question. And the other question is, what is the variance of the triple point in the Al2SiO5 phase diagram? Same question. But in the first question, he does not specify Al2SiO5. He does not let out the composition. So that is why when I ask you, what is the variance of the triple point where sillimanite and lucite kyanite is there? The first thing that you should ask yourself, or the teacher, what is the composition of sillimanite, kyanite and andalusite? What is the composition? Because without the composition, you will not be able to find out C. You will not be able to find out system components, that is C. Impossible, you will not be able to find out. Okay? Okay, what I will do is, I think we will stop here because I think the next, I don't want to have a break. So we'll stop it and the next you see in my 4th video lecture. Yeah? Thank you.